Today we're going to take a look at section 7.2, which is operations on decimals. And we're going to start with the operations of addition and subtraction. So when we are adding and subtracting decimals, the general rule of thumb is to line up the decimal point and then add or subtract as with whole numbers. Every now and then I have somebody who tells me like normal. That's not a good description. What is like normal supposed to mean? Okay, it's the same way we do with whole numbers. And everything that we do in this section feels very natural and normal for you because you've been doing it for a long time. But what I'm going to be doing throughout this section is justifying why it works based on the fraction stuff we did in chapter 6. Okay? So this says, why does it work? Right? So in theory, according to what I've told you, what should happen is I should be able to, oops, not use that color, line them up. So this is 4 and 33 hundredths plus 3 and 26 hundredths. I line up the decimal points like that. And then I would add the same way that I do as with whole numbers. For those of you who've had number theory, you know that there's lots of ways to add. The one that we naturally fall into at some point over time is doing it sort of the traditional standard algorithm, starting on the right-hand side. 3 plus 6 is 9, 3 plus 2 is 5, and then 3 plus 4 plus 3 is 7. Okay, so that's what this method just described. But why does it work? Well, the reason it works is because the 4 and 33 hundredths is really 4 and 3 tenths and 3 hundredths. That's the place value information that you worked on in section 7.1, right? Breaking it apart and writing it by the value that it's in each place value itself. And then we're adding to that 3 and 2 tenths and 6 hundredths. Okay? And then what we did when we were working with fractions is we said, okay, well, fractions will add together very nicely when they have common denominators. And in particular, these two have common denominators. So I have 3 tenths and I have 2 tenths, so that's 5 tenths. I skipped my whole numbers. Let me go back and grab those. Didn't mean to. I have a 4 and I have a 3 here, so that's 7. And then I have my last ones that are not circled at this point. We'll do blue. That have the same denominator, 3 hundredths and 6 hundredths, which gives me 9 hundredths. And of course, you can see that I chose this in particular because it's easy to put back in my standard form. I don't have to do any like shifting things around to justify it. It works for any number, but this one's a nice one to see it in. So this is 7 and 5 tenths and 9 hundredths, or 59 hundredths. So that's why it's working. Okay. So we're going to keep kind of working. This works for addition or for subtraction. It doesn't matter which one you're working with. And so there's the example of addition kind of in the justifying the why. And here's an actual example of when it's used in the real world. And this one's a subtraction problem. It says the stock's price dropped from $63.28 per share to $27.45 per share. What was the loss on a single share of stock? So this is asking us, of course, to subtract. And if we're using the information from the previous slide on what we're able to do, we're going to line up the decimal points. So 63 and 28 hundredths. And we're going to subtract 27 and 45 hundredths. So if I start on the far right, 8 minus 5 would be 3. And then, of course, 2 minus 4 is not possible. So what do we have to do? We have to borrow or regroup. We're going to mark out the 2. And what are we going to change the 2 to being? A 12. And we're going to do that by changing the 3 next to it and making it a 2, right? That's the adjustment or the regrouping that we use. By the way, regrouping is like the catchphrase for children right now. My kids have no idea. I mean, they don't have no idea because I use it around them. But borrowing is just not seen in the curriculums that my kids are using right now. They use the phrase regrouping, which is actually a great phrase. And so just so that you're aware, that's sort of the catchphrase you see these days. 12 minus 4 gives me 8. And then, of course, I've got the same problem I just had. 2 minus 7. So I will regroup. The 6 will become a 5, and my 2 will become a 12. So then 12 minus 7 is 5, and 5 minus 2 is 3. And anytime we're dealing with problems that have context, like units, we need to make sure that our answer includes that same context as part of the answer. So in this case, we're talking about dollar amounts, so we'll put our dollar sign on there. So our answer is $35.83, or 35 and 83 hundredths. Okay, so addition and subtraction. It's very interesting because addition and subtraction with decimals is by far easier than multiplication and division. But that's exactly the opposite for fractions, right? With fractions, multiplication and division is way easier with fractions than the addition and subtraction is. So you do get the addition and subtraction here sort of as the first idea and being easier. So let's talk about what happens then with multiplication. With multiplication, we multiply as with whole numbers. Again, not multiply like normal, but as with whole numbers. And then we count the number of places after the decimal point in all factors. And this will be the number after the number of places after the decimal point in your product. Okay, so the lining up the decimal points with addition feels very natural, and you can even argue to children very much by a decimal point perspective. Look, it's the tenths place, so we're adding up the tenths place. It's the hundredths place, so we add up the hundredths place. We can't add the tenths and the hundredths at the same time. Like, there's an argument there that can be made and seems very clear and justifiable. This feels a little bit like waving of the hands magic. I count the number of decimal places, and then I put a decimal point in there. Like, what's going on? It's not at all intuitive that this should work. It does, it is correct, but it's not intuitive and it's not very easy to justify why it works using decimal points themselves. So let's give the answer using this algorithm, if you will, or this way of doing it. So I'm trying to multiply 3 tenths and 7 tenths. It says I should just multiply 3 times 7, my non-zero numbers, and I would get a 21, right? And then what it's telling me to do is to count the number of place values after the decimal point. So there's 1 on the first number and there's another 1 on the second number, so that's 2 decimal points. So I have to have 2 digits behind my decimal point, which means the decimal point must be here. And if you want to put a 0 in front of it, if that makes you feel better, you can. If you don't care and you don't write it, I'm good with it as well. It doesn't matter. Okay? So this is what this is being argued. It's being argued that this is what I should do. But it's really kind of weird to describe that that actually makes sense and works. So let me show you from the perspective of fractions again why that makes sense. All right, so 3 tenths in fractions looks like this, right? And 7 tenths in fractions looks like this. And if I were to multiply these from what I know about fractions, what would I do? Multiply straight across the top to give me a 21, straight across the bottom to give me 100. And the way that I write 21 hundredths as a decimal will be the exact answer I just wrote a moment ago. 21 ending in the hundredth spot. Yeah? And you can do that with any kind of, like there's nothing special about 3 tenths and 7 tenths. That's just numbers I chose. I mean, I could have given you a tenths one and a hundredths one, and we could have done it the same thing. We still would have ended up with 3 decimal points, okay? The one thing to be aware of, let me give you a careful kind of thing, is that sometimes students will get confused when you're arguing about this from a fractional standpoint. I'll do it as the fractions first. We'll do this one. And of course, this is 20 hundredths, right? Like that, we're good with that. And so it should be written like this, but we tend to sort of not write this one. And it kind of looks like there's only 1 decimal point, right? 1 place after the decimal point, I mean, right? Because it looks like it's 0.2. So just be aware that we still have to consider the whole value of the number. And yes, you can drop the 0 afterwards, but it doesn't erase the fact that there's really 2 decimal points that are occurring because I've multiplied the 100 times the 100 in the denominator. Okay? All right, let's take a look at what happens with division. Division's a little different. What we want to do in general with division, your method you've used probably in the past, is to make the divisor, the number you're dividing by, a whole number by moving the decimal point in the divisor and the dividend an equal number of times, and then divide as with whole numbers. So again, this looks like we're just shifting the decimal points around. Okay, I'll just move all my decimals. Okay, but why is it working? So what it's saying I should do is that if I'm trying to divide 0.75 by 0.5, that what I should do is I should make this a whole number on the outside of the division. In other words, I should move the decimal point one place to the right. But if I do that on the outside, I have to do it on the inside as well, right? I'm compensating. And so what happens is that this changes it to being divided by 5, and I'm dividing the number 7.5 by 5. Okay, is everybody good with the change I made? That's what this is trying to tell me, this language. And then I divide like normal. I say, how many times does 5 go into 7? Like normal, see I did it too, like with whole numbers. How many times does 5 go into 7? One time. Of course, 1 times 5 is 5, and I subtract to give me a 2. And I rather ignore the decimal points for now, and I've got the number 25. So how many times does the 5 go into 25? 5 times, and if I've lined them up as I've been working, the decimal point should just rise to the top and be located in between. That's the way in which we do the problem. But again, why does this work? Well, what we're saying that we're doing is we're dividing 75, this one looks a little different, but I'm still using fractions. We're dividing 75 hundredths by 5 tenths, right? This is just the fractional view of those two numbers as a division step. So what am I really doing when I move a decimal point to the right in that number? Yeah, say it louder, Alicia. You're really multiplying by 10. That's what allows you to move the decimal point, right? If I multiply by 10, I move the decimal point 1 to the right. So what I'm really doing here is I'm multiplying by 10, and if I do it on the bottom, I have to do it on the top. So that justifies why both the decimal points move one unit to this, or one place to the side at the same time. And I end up with, of course, the same values that I had just a minute ago when I rewrote them, 7.5 divided by 5. And then I'm back at the same point. So what I'm trying to justify is why I'm allowed to do this, to change it to be divided by 5. And it's because I'm really just multiplying by 10 on the top and the bottom. All right, no discussion about decimals would be complete if we didn't talk about one of the very common places where decimals are used. Especially within the curriculum that kids this age are encountering, and that's in science classes for scientific notation. So scientific notation has the form a times 10 to the n. The value of a is between the numbers 1 and 10. It could equal 1. It can't equal 10. Do you see the inequality, how it's written there? Okay. Usually it's something in between flat out, but... and the n value is an integer. So if you'll remember, integers means it's positive or negative. That's fine. Or it's 0. But it's whole values. So that exponent can't be a fraction or a decimal or anything like that. It's like 5 or a negative 2 or something. Okay? And it could be 0. It's just not usually 0 because scientific notation isn't necessary if it's a 0. It's silly. Okay? All right. So there are two directions that you have to be able to go with scientific notation, both moving from standard notation into scientific notation and moving from scientific notation back into standard notation. And one of the common ways that people describe this is about shifting decimal points to the left and to the right. I don't like to use that language, and the reason that I don't is because then you have to be very careful about which one you're shifting from and to. Am I starting in scientific or I'm starting in standard? So which one is it? Is it left or is it right? Well, left is this one when it does the... I don't want to think like that. That makes it way more difficult to think about it than to actually look at what's happening to the numbers and make sense about it in the particular problem you're looking at. So let's take an example of one where we're going from standard into scientific. So we are going to move decimal points. All right, we're definitely moving decimal points, and we're moving it to place the value, place the decimal point in such a way that the value I get is a number between 1 and 10. Okay, so I'm just going to stick it in there wherever it needs to be so that I end up with a number between 1 and 10. And there's a one and only one way to do that in any problem. You don't have choices, okay? And then we figure out how many places I moved the decimal point. Did I move it 3 times? Did I move it 5 times? Did I just move it 1 time? How many locations did it actually shift? And that's my exponent. So if I shifted it 3 places, the exponent's a 3. The only kicker you have to decide is it a positive 3 or a negative 3? Positive numbers, exponents, positive exponents, correspond to large numbers. Okay? And negative exponents correspond to small numbers. So can you think about some of the science classes? I know you guys have to take 2 different science classes with Dr. McWilliams, right? And you've had plenty of science in high school. Where have you seen scientific notation used within your science classes? What kinds of values? Very large or very small? Can you somebody else give me an example of a very large number where scientific notation might be used? Something you might calculate as being very large. Okay. Let me rephrase my question. You're exactly right. I mean a context, like where you might, what kind of context might end up giving you a number like that?
I'm trying to measure something.
Okay, what might you be measuring that would give you a big number like that? Okay, so measuring how much something weighs, and it would have to be something really like big, right? So if you were measuring like the weight inside of a swimming pool or something, right? The weight of the water in the swimming pool, that'd be a big number. Can you give me another example? That's a good example. It doesn't usually show up in science. There's something else that's a little bit more common in science that shows up. Distance is a really common one. Can you give me an example of a distance, Julie, that might make sense? Yeah, the distance between planets and the sun. Distances are a really common place where you see scientific notation used. So those are an example of something really, really big. Can you think of something in science that's really, really small where you see scientific notation used? Yeah, atoms and electrons and stuff like that, right? Like chemistry kind of stuff? Yeah, definitely something on the smaller end of the spectrum. Okay, so positive exponents mean large numbers, like distances between planets. And small, okay, or negative exponents mean small numbers, like the atoms and things like that. Okay, so let's take an example of one, and we'll figure out what it is we need to, where it is we need to put our decimal point, and what we need to do after that. So here's our number, 298,000. Where should the decimal point go? Between which 2 numbers? The 2 and the 9. So the decimal version of this number that I need right now is a 2, the decimal point, and then 98, 2 and 98 hundredths. Of course, that's not equal to the number I started with. So I have to continue with the rest of the scientific notation to make it equal. So let me go back up to where the digits originally were. It was originally over here. And it's moved over here, right? How many times, if it did single jumps, did it have to move to do that? How many? 5. So here's 1 move, 2 moves, 3 moves, 4 moves, 5 moves. So my exponent is a 5. And the last thing I have to decide is simply, is it a positive 5 or a negative 5? Well, I look at the original value and I ask myself, is it a large number or a small number? And the answer is, it's large. And so how do I decide? Like, I mean, there's some relative, like what's large? What's considered large? Well, anything bigger than 10 is large. Anything smaller than 1 is small. And that's the deal. This is a large number, right? I mean, let's be honest. If somebody gave you this much money, you'd be pretty excited, right? It'd be a large amount of money. No question. So this exponent will be what? Positive or negative? Positive, because it's a large number. So this is the scientific notation for this particular number. And if you want to write yourself a note to the side, it's positive because 298,000 is large. That's how we decided. We want to be able to go the other direction as well. We want to be able to take something that's in scientific notation and turn it into standard notation. Okay? So, it's quite similar. We're moving decimal points, right? We're moving the decimal points. The number of moves is based on the number or the size of the exponent. Right? Is the exponent of 5 or is the exponent of 4 or is the exponent of 10? That tells you how many moves you make. Again, I don't talk about moving it left or right. I talk about, will the number be big or small when I'm done? If it's a positive exponent, the number will be big when I'm done. If it's a negative exponent, the number will be small when I'm done. Positive exponents are large numbers, and negative exponents are small numbers. So when we did this problem back here, we kind of made the decision about the positive negativeness of the exponent at the end, right? It was the last thing we did by asking ourselves, is it small or is it big? But when we're looking at a number that's already in scientific notation, we need to know that at the beginning in order to make the decisions about how our decimal point is going to shift. Is it going to become bigger or is it going to become smaller looking? So is this a positive or a negative exponent? It's negative. And a negative exponent means that I'm going to have what kind of a number? A small number. So right now, I've got this decimal point between the 3 and the 2. Which direction is my decimal point going to have to move if I'm going to make this a small number? To the left, yeah? It's going to have to move to the left. And how many places will it have to move? 5, because it's a number 5. So I can put zeros, as many as I need, on here, and I can move it 5 places. So here's 1, 2, 3, 4, 5. I happen to still have a 0 in front. You don't have to have that there. But there are 4 zeros between where my decimal point landed and my 3. So I have 1, 2, 3, 4, and then I have a 3, 2 at the end. Any questions on that shift? Okay, so what happens when we're actually operating with scientific notation, like operating on scientific notation type numbers? So here's an example. It wants us to write the result of the following in scientific notation. It is not in your best interest to change both of these into standard numerals. These are both big numbers, right? With lots of zeros on the end. I mean, they're power of 12 and power of 15. And if you try, your calculator is going to freak out on you. It's going to be like, what are you doing trying to put all these places in here? I don't know what to do about this, right? It might even give you an error. It might turn it back into scientific notation, and that's okay if you want to verify that you've done the problem correctly, but it still won't show you the work in between that I expect to see too. So what do? Well, we've talked about the fact that our number systems that we work with, if you've been in number theory, are commutative anyway, and we talked about it last time in fractions. So commutative just means you can change the order. In other words, I don't have to have this as 8 times 10 to the 12th. I could change this 8 times 6 and then 10 to the 12th times 10 to the 5th. I can regroup, I can reassociate. This is the associative property as well because I'm changing what's inside of which set of parentheses. But changing the order is the commutative property, so I've got all those great properties. And I can actually multiply it piece by piece. So what is 8 times 6? 48, you got it. And then what happens when I multiply 10 to the 12th and 10 to the 15th? Do you remember? Yeah, I add the exponents. So this will be 10 to the what power? I think you guys are saying 27. Is that right? Awesome. Now, it's very tempting to stop here because you did the multiplications that it asked. But why is it not okay to stop here? 48 is a whole number. I think you mean a different word.
I
Okay.
Yeah, there's no one.
Okay. There you go. Okay, so the number that I've got, the 48, yeah, you guys are getting it all together. Good job. The number 48 is not between 0 or between 1 and 10, right? It's not because it's not a decimal, because if the number left had been a 4, we'd be okay with that. But it's because it's actually bigger than 10, and that's the problem. So whoever said it needs a decimal between 4 and 8, you're exactly right. That's exactly where it needs the decimal. There needs to be a decimal point like this. But of course, you can't just like willy-nilly move around your decimal points and not change the number. I mean, that changed it, right? So what do I have to do, to compensate? I've got too many things going on here. Let me put an X here for my multiplication. Well, I compensate it by figuring out what I have to do to change my exponent. That's thick. So, 48. Is that a big number or a small number? It's a big number. So my exponent needs to be bigger than what it was before. How many places did I move my decimal point? 1. So I changed my exponent by that same amount. It's a 28 now. If for some reason when I multiplied, let's just say for the moment that I had ended up with this number when I was done. Okay, I obviously did not, so please sort of write this to the side and don't confuse yourself. But I still would have had to move it, right? I still would have had to make it 4.8. But because the number was a small number when I started with, right, the exponent would become 1 smaller by making that adjustment. Are you guys with me? There's a direct relationship between those. And that's where we're going to stop for today.